Have you ever wondered what is actually happening inside an AI model before it can answer your questions, write your emails, or explain a complicated topic? Large language models do not come preloaded with intelligence. They are trained, and that training process is one of the most significant engineering efforts in the history of computing. In this video you are going to understand exactly how it works, from an empty model to the AI tools you use today, and you will not need a single equation to follow along. First, it helps to understand what a large language model actually is at its core. It is a computer program that takes in text and predicts what text should come next. That sounds almost too simple, but it turns out that if you get extremely good at predicting the next word, you end up learning an enormous amount about language, facts, logic, and reasoning. The training process is basically a long, expensive exercise in making the prediction engine as accurate as possible. Before any training can start you need data, and the amounts involved are hard to wrap your head around. We are talking hundreds of billions to trillions of words. Teams collect text from public websites, books, academic papers, code repositories, and other written sources. The goal is to expose the model to as much of human knowledge and language as possible. More data generally means a smarter model, but only if that data is reasonably clean and diverse. The raw data that gets collected from the internet is messy. It contains spam, duplicate content, toxic language, and low-quality text. So engineers run the data through filtering pipelines that remove or downweight the bad material. This cleaning step is less glamorous than the training itself, but researchers have found that the quality of the training data has an enormous influence on the final model. A model trained on cleaner data consistently outperforms a model trained on more but dirtier data. Once the data is cleaned, it goes through a process called tokenization. The model does not read text the way you do, one letter or one word at a time. Instead, it breaks text into chunks called tokens. A token might be a whole word, part of a word, or a punctuation mark. The vocabulary of a typical large language model contains somewhere between 30,000 and 100,000 unique tokens. Every word or phrase you type gets converted into a sequence of these numeric tokens before the model ever sees it. Now we get to pre-training, which is the most expensive and time-consuming part of the whole process. During pre-training, the model sees a token and tries to predict the next one. It makes a guess, compares that guess to the actual next token, measures how wrong it was, and then adjusts its internal settings slightly to do better next time. This cycle repeats billions upon billions of times across the entire dataset. The internal settings being adjusted are called weights or parameters, and a large model can have hundreds of billions of them. The reason this works is a concept called backpropagation. When the model makes a wrong prediction, the error signal travels backwards through the network layer by layer, nudging each weight in the direction that would have produced a better answer. Do this enough times across enough data and the weights start to encode real patterns. The model learns grammar without being taught grammar rules. It learns facts without being given a textbook. It learns cause and effect simply by seeing what words tend to follow other words in context. At the heart of every large language model is an architecture called the transformer. The transformer was introduced in a 2017 research paper and it changed the field permanently. The key idea inside a transformer is something called the attention mechanism. Attention lets the model look at every token in the current context and decide which tokens are most relevant to predicting the next one. When you write a long sentence, the model is not just looking at the last word. It is weighing the importance of every word that came before. The transformer is made up of many layers stacked on top of each other. Each layer processes the input and passes a richer, more refined representation forward to the next layer. Deeper in the network, the representations become more abstract. Early layers might capture word relationships. Later layers capture concepts, facts, and reasoning patterns. The depth of the network, combined with the attention mechanism, is what gives large language models their ability to handle complex questions. Scale plays a dramatic role in how capable a model becomes. Researchers have found that making models larger, giving them more parameters, training them on more data, and using more computing power, leads to predictable improvements in performance. This relationship is described by what are called scaling laws. It is one reason the major AI laboratories keep pushing model sizes higher, even though the cost of training the largest models can run into tens or hundreds of millions of dollars. The hardware used for pre-training is almost entirely graphics processing units, or GPUs, though specialized chips called TPUs are also used at some labs. Training a frontier model requires running thousands of these chips in parallel for weeks or months. Coordinating that computation is an engineering challenge on its own. The chips need to stay synchronized, the data needs to flow without bottlenecks, and if one machine fails, the training run has to recover without losing too much progress. After pre-training, the model is technically capable but not yet useful to most people. At this stage it is essentially a very good text completion engine. If you prompt it with the beginning of an article, it will continue that article. But it does not know how to follow instructions, answer questions helpfully, or decline harmful requests. That is where fine-tuning comes in. Fine-tuning takes the pre-trained model and continues training it on a much smaller, carefully curated dataset of examples that demonstrate the behavior you want. There are different approaches to fine-tuning. Supervised fine-tuning shows the model examples of good question and answer pairs written by human contractors. The model learns to mimic that style and those conventions. This step is far cheaper than pre-training because the dataset is much smaller, but the quality of the examples matters enormously. The human writers crafting these examples are essentially teaching the model what a good response looks like. This is where reinforcement learning from human feedback comes in, often shortened to RLHF. Rather than showing the model a perfect answer, RLHF works by generating several different responses to the same prompt and then asking human raters to rank those responses from best to worst. A separate model called a reward model is trained on those rankings to predict which responses humans would prefer. The main model is then trained to produce responses that score highly according to the reward model. RLHF is what turns a raw text predictor into an assistant that sounds helpful, avoids harmful content, and tries to give accurate answers. It is also imperfect. The reward model is trained on human judgments, and human judgments can be inconsistent, biased, or easily satisfied by confident-sounding responses that are actually wrong. This is one reason large language models can sometimes produce text that sounds authoritative but contains errors. The training signal rewards sounding good, not necessarily being correct. One of the most important limits of the current training approach is what researchers call the knowledge cutoff. The model only knows what was in its training data, and that data was collected up to a certain point in time. Ask the model about events that happened after that cutoff and it either will not know or will make something up. This is why many deployed models are now paired with tools that let them search the web or access current databases in real time. Another significant limit is called hallucination. Because the model is fundamentally a prediction engine trained to produce plausible text, it can generate confident-sounding statements that are simply false. It does not have a fact-checking mechanism built into the core architecture. Researchers are actively working on ways to reduce hallucinations, including training techniques that reward the model for saying it does not know something rather than guessing. There is also the question of what the model does and does not understand. Large language models are extraordinarily good at manipulating language, but whether they have genuine understanding or are doing something closer to very sophisticated pattern matching is one of the most debated questions in AI research today. Practically speaking, what matters is what the model can and cannot do reliably, and training determines both of those things. Newer training techniques continue to push the boundaries of what these models can do. Constitutional AI is an approach where the model is trained to evaluate its own outputs against a set of principles and revise them before responding. Instruction tuning, chain-of-thought training, and tool use training are other active areas. The core loop of pre-training followed by alignment-focused fine-tuning remains the dominant paradigm, but the details are changing rapidly. To summarize, training a large language model happens in two broad phases. Pre-training is where the model learns language and knowledge by predicting the next token across a massive dataset, adjusting hundreds of billions of weights through backpropagation. Fine-tuning and RLHF are where that raw capability is shaped into a useful assistant by showing it good examples and training it to produce outputs that human raters prefer. Both phases matter, and the quality of the data in both phases shapes the final model more than almost any other factor. If this explanation helped you finally make sense of what large language models are doing under the hood, hitting the like button takes 1 second and it helps this channel reach more people who want real explanations without the hype. Subscribe so you do not miss the next video, where we are going to go one level deeper and look at how AI agents work, meaning how these same models are being combined with tools, memory, and planning systems to take actions in the real world, not just generate text.